All right, so which of the following limits is equal to the definite integral from 1 to 6 of x cubed dx? We developed this idea with Riemann sums. So let's go back and kind of revisit what that would look like with Riemann sums. X cubed, again, is this parent function. It looks like that. What we were doing is we were approximating it using subintervals. So if we're going from 1 to 6, first of all, that's from here to here. Let's go ahead and think about what we did. Let's just say I used n equals 3 subdivisions, something like that. I'll just draw it like that. We have 3 subdivisions. So we're trying to find the actual area down here. Remember, the way it worked is we needed to find our delta x. I needed to figure out what the width of each interval was. So how do we figure out the interval width? We did b minus a over n. B is your right endpoint, A is your left endpoint. You subtract them, you get your total width. You divide it by n, the number of subintervals. So for us right here, it's going to be 6 minus 1 over 3, which is 5 over 3. But in general, it's going to be 6 minus 1 over n, or 5 over n. So this is your delta x. Because we don't really want to use n equaling 3. We want n to go to infinity. Remember, the more rectangles we use, the closer the approximation becomes the actual. So now I know that if this is my starting value, there's 1. This one is plus a delta x away. This one is plus 2 delta x's away. This next one will be plus 3 delta x's away. So let's go ahead and set it up. The areas are going to be the following. They're going to be the function values, the f of x sub i's, times your delta x's. Remember, that's just your height times your width. Your height times your width. Well, the function values are going to be f of, if you look at your answer choices, they're all starting at 1. And then plus, how do we go from delta x to plus 2 delta x plus 3 delta x? Those are just multiples of delta x, right? So that's going to be plus 5 over n, the width. And notice, if you look at all your answer choices, this is the sigma. They use k as the variable. K is just a counter. 1, 2, 3, 4, 5. So if I want to get multiples of 5 over n, that's just 5 over n times k. 5 over n times k. So when k is 0, I'm at the left endpoint. When k is equal to 1, I'm at the next stopping value right here. When k is 2, I'm 2 delta x's away, so on and so forth. So really what this is your starting value. And then this is plus multiples of delta x, which is b minus a over n. So that gives you the y values, and then times delta x. What is our delta x? It's 5 over n. So this is your delta x, your width. And if that gives you the area of any single rectangle, all you have to do now is do what with those? Add them up from k equals, and they're all going to be the same. They're from 1 to n, and then you take the limit as n goes to infinity. And what that last little step does, that's the calculus step. That's what turns the Greek letter S, sigma, that looks like an E, into an integral symbol, which still stands for sum. All right, so now you can look for that as an answer choice. Do y'all see that there anywhere? D? Oh, yeah. I didn't actually apply it to my function. This is still generic. This is f of. What is our function? Our function is x cubed, right? So let's go ahead and apply that. We'll take the limit as n goes to infinity. Yeah, thank you, Jovan. That could be any function. If it were like sine of x, you would plug that into sine. This is x cubed, so it's going to be that thing cubed times 5 over n. And so, Jovan, you thought it was D? D is the right answer, yeah. D is the right answer. So in the future, you don't necessarily have to do all that work. You could just kind of look at it and tell, right? We're starting at 1. We're going from 1 to 6. So these all have to start at 1. So that doesn't eliminate any of them based upon that. So then you can figure out your delta x. Your delta x is b minus a over n. That's 6 minus 1 over n. That's 5 over n. So that's enough to get rid of several of them because it has to be here. This has to be multiples of delta x times k, and this has to be delta x. So those have to match. These match right here. These don't match. These don't match. These match. They're both 1 over n, but guess what? They're not 5 over n, so that's out. So that has to be the answer. So based upon that and that alone, you can kind of figure it out. So let's do one more real quickly here. Go ahead and write on your own a sigma notation for the following integral. The integral from 3 to 7 of sine of x dx. Go ahead and write a sigma notation. I'll start you off. It's going to be the limit as n goes to infinity. If they don't use k right there, they can usually use I, j, or k. I'll use I this time, from I equals 1 to n. So instead of having multiples of k, you can have multiples of I. Go ahead and figure it out. All right, let's see how you did. First thing you want to do is calculate delta x. We're going from 3 to 7. So 7 minus 3 over, in general, n is 4 over n. That's very important, and we're starting at 3. So our function values are the heights. That's going to be the function value, which is sine of 3 plus multiples of delta x. So 4 over n times I, or 4i over n. You could put the I in the numerator. And then times delta x, which is 4 over n. This is your width. And that's it. That's the answer. We used I instead of k. So what matters is this here, because that's just a beam counter. 1, 2, 3. It's multiples of I. Now, one last thing here. When we do it this way, are we taking the limit of the right endpoint or the left endpoint method? Well, let's see. When k equals 1 and you plug it in here, your first x value is 1 plus delta x. So if I'm starting at 1 and I go another delta x, I'm using this as the height. So I'm going back this way, and then I'm doing this. So this ends up being the what? It's the right endpoint method. Yeah, it's the right endpoint method. There's a real easy way to turn this from a right endpoint method to a left endpoint method. All you have to do with sigma notation is if I let this start at 0 instead of 1, now what do you get when you plug in a 0 for k? You get 1 plus 0, which is now using 1 as the first y value. So that would be the left endpoint. So the nice thing about this is if you had a question like this, all of those k's or i's or j's are going to be the same. Okay? So it's just a matter of saying starting value plus multiples of delta x times delta x. Okay? So this has been showing up in the last few years. And this just goes back to the idea of Riemann sums. And that concludes 6.2. So this worksheet will be due on Wednesday. And we're going to start 6.3, the last section, tomorrow. It's a big section. There's 3 big ideas in it. But it is the last section of the year, kind of bittersweet.